Hello everyone, this is Chandrasekhar welcoming you all to this wonderful and beautiful Ground Zero series for civil and mechanical engineers. As you guys all aware that in this series we bring the most important concept and try to make it simple and easier for you to understand through animation. So in today's session, I will be discussing about one of the important concept of the subject heat transfer, that is very common topic which is frequently asked in your examinations as well, which is conduction in composite wall. So before I start, let me quickly introduce myself. I am having more than 10 years of teaching experience in GATE, IES and PSUs. Also cleared engineering services examination and worked in sale also for a couple of years. You can connect with me through the mail ID which is there on the top of the screen, and you can join me on the Telegram as well. That is Mechanical by Chandrasekhar. The link is also there on the bottom of this screen. So let us start talking about the conduction in a plane wall. When we talk about a plane wall or a plane surface, the area of the surface will be constant. The area which is perpendicular to direction of conduction will be constant. All right, and we are talking about one-dimensional conduction. There is no heat generation, and the heat stored will also be zero. Q stored will also be zero. So the inner face temperature is T1, which is higher compared to the outer surface temperature, which is T2, which is lower. If T1 is greater than T2, then the heat will flow in the material in the plane wall through conduction from left to right, from high temperature to low temperature. And for conduction, we can use the Fourier law of heat conduction. So according to Fourier law, we can say Q is equal to minus K into A into dt by dx will be constant. The rate of heat transfer will remain constant because there is no heat generation in the system. There is no change in internal energy in the system. All right. So from here we can say dt by dx will be constant, and when the temperature variation in x direction, in the direction of heat flow, will be constant, the temperature profile will be linear in the plane wall. When the conduction is one dimensional, steady state, no heat generation. So the temperature profile, this is the higher temperature T1 and this is the lower temperature T2. So the temperature profile will be linear, and dt by dx can be replaced by delta T by delta x, and delta x is the thickness of the plane wall. So our expression for conduction in a plane wall where the area is constant will become K into A into delta T by L, which will be constant. All right. Now the same analysis can be related with the circuit diagram. The way we draw the electric circuit, we can draw the thermal circuit as well. So the analogy between electrical circuit and thermal circuit is the voltage will be replaced by the temperature here, current will be replaced by the heat transfer, and electrical resistance will be replaced by the thermal resistance. And according to Ohm's law, current flow is equal to voltage drop divided by electrical resistance. We can, in the similar manner, we can say Q is equal to delta T, that is thermal potential, temperature difference upon thermal resistance. All right. So if we relate it with circuit diagram, we can write it as delta T upon L by Ka, isn't it? So if we draw the thermal circuit diagram, the thermal resistance is RTH, inner surface temperature was T1, outer surface temperature T2, heat transfer rate was constant. So this is called as delta T. This is called as delta T. So we can equate it with delta T upon thermal resistance. So what will be the thermal resistance? So the thermal resistance becomes L by Ka, where L is the thickness of the plane wall, A is the area normal to the direction of conduction, and K represents the thermal conductivity of the material of plane wall. Now, if we talk about composite plane wall, what is a composite plane wall? When a wall is made up of more number of materials, it becomes the composite wall. So the composite plane wall can have a series combination of materials. When do we call it to be series combination? When one material is joined with another material one after another, and the direction of heat flow will be from left to right. That represents the composite plane wall having the series combination of thermal resistance. One thermal resistance will be for the first wall, the second thermal resistance will be for the second wall, and they will be connected in series. That is called as series combination. This is one material, this is another material. Thermal conductivity of 1 and 2 are given. The thicknesses are given as L1 and L2. The direction of heat transfer will be from left to right, and Q will remain constant because there is neither any heat generation nor any heat storage. So if we draw the circuit diagram for this, then there will be two thermal resistance. For R1, it will be L1 by K1 into A. The area which is perpendicular to the direction of conduction will remain same for material 1 as well as material 2. And this R2 will be L2 by K2 into A. These will be the value, and Q will remain constant. The thermal potential across R1 is delta T1, and the thermal potential across R2 is delta T2, and the overall thermal potential between R1 and R2 is delta T overall. So from here we can say Q, because the resistances are connected in series, so Q will be equal to Q1 is equal to Q2 is equal to Q will remain constant, and the overall thermal potential will be equal to delta T1 plus delta T2 plus delta T3 and so on. If we use the Ohm's law, Q is equal to delta T upon thermal resistance, isn't it? So delta T overall can be written as Q into R equivalent. Q into R equivalent will be equal to delta T1 can be written as Q1 into R1 plus delta T2 can be written as Q2 into R2 and so on. So because Q is equal to Q1 is equal to Q2 for series combination, this Q1, Q2 getting cancelled out, and for series combination we will get equivalent thermal resistance will be sum of R1, R2, R3 and so on. For two resistances, R equivalent will be simply R1 plus R2. That is the equivalent thermal resistance, and we can say Q is equal to overall thermal potential divided by R equivalent, that will be equal to Q1, that is delta T1 upon R1 is equal to delta T2 upon R2. From here we can find out the thermal potential ratio across R1 and R2 given by this expression. That is for series combination of resistances. The composite plane wall can have the parallel combination as well. What exactly is the parallel combination? When the materials are connected, the materials are connected with each other simultaneously like this. The conduction will be taking place from left to right. So there are two materials which are joined simultaneously. Or we can say the inner surface temperature and the outer surface temperature remain same for both the materials. Then it is called as parallel combination. You can see over here, the direction of heat transfer will be from left to right. The inner surface temperature of material 1 and material 2 are T1, and outer surface temperature of material 1 and 2 are T2. The thickness will remain same. For both the materials, thickness will be same. So some part of heat flow will be taking place in 1 and some part of the heat flow will be taking place in the material 2. That is known as parallel combination of plane wall. If we draw the circuit diagram, then for two materials there will be two resistances, thermal resistances, which will be drawn in parallel. What is R1? L upon K1 into A1. A1 is the area of the material 1. This is A1, and R2 will be equal to L upon K2 into A2. the direction of conduction will be from left to right. Q1 will be across R1 resistance and Q2 will be across R2 resistance. So from the parallel resistance, parallel circuit diagram, we can say Q is equal to Q1 plus Q2 plus Q3 and so on. And overall thermal potential, delta T overall. Overall thermal potential will remain same. This is T1, this is T2. So delta T overall will be equal to delta T1 is equal to delta T2 is equal to so on. From the equation number 1, Q can be written as, because we know Q is equal to delta T upon thermal resistance. So Q can be written as delta T overall upon equivalent thermal resistance is equal to, what is Q1? That is delta T1 upon R1 plus delta T2 upon R2 plus so on. So because overall thermal potential is same as delta T1 is equal to delta T2, so the relation for equivalent thermal resistance is given by this expression, isn't it? 1 upon R equivalent will be equal to 1 by R1 plus 1 by R2 and so on. For two resistances R1 and R2, we can say R equivalent will be equal to R1 into R2 upon R1 plus R2. That is for two thermal resistances which are connected in parallel. So from delta T overall, which is equal to delta T1 is equal to delta T2, we can say Q is equal to delta T upon thermal resistance. So for delta T overall, we can write Q into, or sorry, right? From this, Q is equal to Q1 plus Q2 plus Q3 and so on. Or we can say, what is delta T overall? That is Q into equivalent resistance will be equal to Q1 into R1 is equal to Q2 into R2. We can write this way, and from here the ratio of Q1 by Q2 can be obtained from the ratio of R2 by R1. That is how the heat flow rate will be distributed in across both the materials, across both the thermal resistances. All right. So that is all from my side for this section. I hope you have enjoyed and understood the basics of composite system having the conduction. All right. So see you in the next such video. Till then, enjoy, take care, have a good day. Thank you guys. Thank you very much.